Test number 1 is on Monday, the 28th. I'm going to wait till after the test to talk about test corrections, but if you get below a B, you can earn back some points to raise your score, but you can't go past 80% past having a B. Okay, I think we want to just finish 2.3. Okay. I don't think we super finished the example I was doing last class, so I'm just going to put it on the board, and then we're getting into a theorem and 2 theorems. Okay, so our example was the limit as x goes to 3 from the right. Of x squared minus 6x plus 10 divided by x minus 3.
Wait, is this the same example from last class?
Yeah, I'm just gonna like summarizing what happened. So we got positive infinity. Okay, then I'm just gonna write down what happened on the right. And what's conclusion? No, that's right. Left. Okay, this one was negative infinity. So the limit as x goes to 3 does not exist. I just didn't know if we had written that last part. Okay, so just wanted to make sure we summarize like what the limit is. And next, I don't think this theorem has a special name, but we have 2 functions, f of x and g of x.
I have a question, Cassie.
Yeah.
Wait, if one's, wait, actually, oh wait, no, never mind.
Okay. Okay. Yeah. Right. So we have if f of x is less than or equal to g of x for x near a, except maybe right at a, and the limit as x goes to a of f of x and the limit as x goes to a of g of x both exist. Then the limit as x goes to a of f of x is less than or equal to the limit as x goes to a of g of x. And we'll draw, I think we'll draw a picture. Nope. We'll try to maybe draw a picture. F of x is less than or equal to g of x. For x near a. Except possibly at x equal to a. Okay. And both limits for each function exist. So the limit as x goes to a of f of x. And the limit as x goes to a of g of x. Okay. Both exist. Okay. Then the limit as x goes to a of f of x will be less than or equal to the limit as x goes to a of g of x. Let's make an example. Let's get units. 1, 2, 3, 4, 5. F of x has values greater than or equal to g of x values. So our function f will be red, and we're going to have like a parabola. Let's have it right with its vertex at 3, 3. Let's do g of x will be, let's just do a curve. We're going to have like a half circle from 1 to 4, touching the x-axis, but just above this, with a peak at usually let's go from 2 to 4 and a peak at 2, 2, like this. It's more like a dome. That's my function g. G sends its inputs to outputs that are less than the outputs for the function f. So let's say you do the limit as x goes to 2. For g of x, it would be 0 as your limit. And for f of x, you'd be at like, maybe it's about 4, approaching 4. Even here, like as x goes to 3, for g of x, that limit would be 2. And for f of x, the limit is greater than that. It's 3. We'll write that one down.
Wait, the point's at 3, 3, right?
Yeah, like for this point,
Yes.
is that 3? Yeah,
It will make
3,
sense.
3.
Okay.
Okay. I could do a bunch of examples. I'm going to just do one for now. We're going to have x go to 3. So the limit as x goes to 3 of g of x is going to be 2. Okay. The limit as x goes to 3 of f of x is 3. Actually, I'm going to replace this and with what we got in that theorem. So that limit 2, it's less than or equal to this limit 3. Okay. And you don't have to like highlight this. It's just my way of like pointing out the part of the theorem.
Wait, does that say limit g is less than or equal to limit fx?
Yeah.
Okay, just want to make sure. Yeah, okay, got it. Wait, how does g equal 2, by the way? Because when x equals, oh, okay, I see, yeah. Yeah, 2, positive 2, okay, I got it. Okay.
Yeah. Okay, we're gonna go on to the next theorem. It's called the squeeze theorem. In this case, for this theorem, we need 3 functions, and each one's less than or has outputs that are less than or equal to the next, the outputs for the next. Okay, if f of x is less than or equal to g of x, which is less than or equal to h of x, for x near a, okay, except possibly at x equal to a. Okay, and we need to know that the limit as x goes to a for all 3 functions does exist. So first one, the limit as x goes to a of f of x. And the limit as x goes to a of g of x. And the limit as x goes to a of h of x. All of the limits exist. They exists. Okay. I think what I should say is if the limit as x goes to a of f of x is equal to the limit as x goes to a of h of x, and we'll call it some number L, then the limit as x goes to a of g of x also will be equal to L. I'm going to erase this then, just an if. All the limits exist. How about and if the limit of f of x is equal to the limit of h of x as x goes to a. going to call that limit L. Then we've squeezed, or yeah, we have squeezed the limit for g of x as x goes to a into a little neighborhood. It's getting, closer and closer to L. Limit as x goes to a. Oh wait. F of x and h of x. And then the g of x was in the middle. And this limit was L. Okay. Start with a sketch of 3 different functions. We're going to start with f of x, and we're going to have L like this. Put A right here. Okay, so I'm going to draw f with green, and we're going to get closer and closer, outputs that are closer and closer to L as x goes to A. But we're going to start down here, kind of swoop up and then back down. It's pretty good. Okay, I'm doing g of x with blue. And it's just kind of like curving a little flat, but not super flat, just a little like swoop this way. And then h of x, I've got red, and we're gonna kind of come down and then back up.
Well, is G a straight line or is it supposed to be kind of curved?
Either way, it's as long as if it's straight, then make sure it goes right through L, but it can be a curve. Okay.
So it's a straight line, okay.
Yeah, we could draw that. Let's draw straight. Okay. Well, it doesn't have to be straight, but I can draw. But it could also like be a little squiggly thing like going this way. Okay, we're getting closer. X is getting closer and closer to A. On the left and on the right. Your function values for F are less than or equal to the ones for G, which are less than or equal to the ones for H. And the limit for h as x goes to a is L. And the limit of f as x goes to a is also L, which means you've squeezed the limit as x goes to a for g of x to also be equal to L, the squeeze theorem. So sometimes, I don't know if you will need it. I think you might use it like a little bit in your homework, but it's something you would use more doing like homework on paper to prove that you know what the limit is by using some other easier to work with functions and then squeezing your messy function in between those two. Let's see, what's next? Okay, so for my plan, what's next is to start the next section, which would be 2.5. So does anyone have any questions about 2.3?
Yeah, I'm usually when we do these kind of examples, I'm always usually confused about what the answer is. So probably next time when you make the answer, can you like put like a circle, like a squared box or something so we can know?
Sure. And I can also draw another picture and make another example. So let's just do another one.
Okay, wait, are we still on this example or are we done?
This one's pretty much done. This is just a picture for like what's happening in the theorem.
Oh, okay.
But so let me summarize this picture with the theorem. It's like a visualization of the squeeze theorem. So we'll write down what happened and we'll do one more example. Okay. We'll figure it out. Okay, so what I draw or have drawn is values for your function f of x are less than or equal to the g of x values, and those all are less than or equal to h of x values.
Keep the graph up. I'm trying to rewrite it.
Yeah, I'm going to keep this graph for now. Okay, and the limit as x goes to a of f of x is L, because your function f as x goes to a, f of x goes closer and closer to L. And I might draw this a little bit closer. It doesn't have to be like perfect. Okay, and then the top function we called h, and the limit as x goes to a for your output of h, that's going to be also L. These outputs are getting closer and closer to L as x goes to a.
Also, it's like they're squeezing together, right?
Yeah. Yeah, so like these limits are getting like this way, and then so the function in the middle has the same limit L. Middle function G. also needs to be, oh. So like maybe your problem has some function that you can't visualize and you don't have time to really try to graph it, or maybe you can't really graph it. But you know, or have a good feeling that its outputs are near L, and maybe you can show that those function values are less than or equal to like this nice function, which you can find a limit for easily, and then same from another function, and like squeeze those results and get your limit for that maybe messy function. I don't know. I think that, again, I think there's only 2 questions that may need the squeeze theorem in homework 2.3, which is due the same day as your test, Monday, the 28th. If you need help, let me know. I think I will draw one more example to make it like actual numbers that we get out, and maybe some easy functions. Yeah. Okay, erase. What could I do? Okay, I feel like we need a little bit of practice drawing trig functions. So this doesn't have to be perfect, but what I'm going for is sine of x between 0 and 2 pi, which is going to start at the origin, have a max at pi over 2, 1, and a min at 3 pi over 2, negative 1. And I'm going to come back to 2 pi 0. Okay, so first pi, 2 pi.
So can you
Okay,
square the
half
answer
pi.
for, wait, no, never mind.
Yeah, just another one for squeeze theorem, totally new.
Yeah.
Yeah. Okay, halfway is pi over 2. Okay, and then between pi and 2 pi is 3 pi over 2. I'm going to make this positive 1, and then you've got negative 1. And let's do 1 cycle for sine of x. So start at 0, 0. We're going to come over here to pi over 2, 1. We're going to curve down through pi 0. Have a min at 3 pi over 2, negative 1, somewhere here. Then the last point we're going to put in here is 2 pi 0. Okay. I'm just going to do a parabola There's a vertex at pi over 2, 1. So right here. And then to represent this like function g of x that's like maybe messy or like hard to graph, I'm just going to do this squiggly line that's going to like cross right through here. And then from the theorem, we've got the function f of x less than or equal to g of x for your x values. So this was my f, the red function, this little one cycle of the sine curve. Okay, then my like parabola guy is black, and we're going to call it h. Its values are greater than or equal to all of the outputs for g and all of the outputs for f. Okay. Yes. So just another example for the squeeze theorem. And again, I've got my function f has outputs less than or equal to my function g, which is outputs less than or equal to that one function h. So I've gotten this, and limit as x goes to pi over 2 of f of x is 1.
So G is L, the curve, the swirly line.
G is a function, and its limit is going to be the L being the number 1.
Oh, okay.
This is a 1. And that's all happening when x goes to pi over 2. Yeah, so just to read it out, the limit as x goes to pi over 2 of f of x is 1. And it's the same as the limit as x goes to pi over 2 of h of x comes down to 1. And that forces the limit as x goes to pi over 2 of g of x, the function that's squiggling through, also must be equal to 1. Okay, I'm going to check the time, and I think we should start 2.5. Oh yeah, wait. There's like 4 minutes, so I'm gonna at least put up the title, and then we can get into stuff next class. So 2.5. It's continuity. I'm going to use these last few minutes to put down that a function f is continuous. At x equal to a. If the limit as x goes to a of f of x is equal to f of a. So that's the definition for being a continuous function at x equal to a. And it means three things. So I'm going to break it down. So this means first, the limit as x goes to a of f of x does exist. Also, f of a is defined. So your function does have an output at x equals a. Okay. And the last thing is this last part here. And the limit of the function as x goes to a is equal to f of a. I think we're out of time. Yep. Okay, thank you everyone. Sorry I was late. Oh, yes, wait, oh no.